Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to conclude our discussion on chapter 11, which is concerned with reaction mechanism. When we left on Tuesday, we were discussing the elimination by molecular reaction. So we are going to start on this today. But before we do that, just a few announcements. I want to remind you that the next class exam is scheduled for next Tuesday. That is November 19. And because of that, we are going to have an online review session, which is a recitation on Sunday. So the online review session will be on Sunday, November 17 at 8 p.m. So I will send all of you the link to that online session. So when you come to the session, make sure you have a copy of the 2012 exam number 3, okay, because we are going to use that exam for that session. Also, for those of you who have not completed the online survey that I sent you, the completion deadline is tonight. That is Thursday, November 14 at 11 p.m. Okay, so let us get this session started. So when we left on Tuesday, we discussed the substitution nucleophilic bimolecular reaction. We also discussed substitution nucleophilic unimolecular reaction, which is SN1. And before we left, we were discussing the elimination reaction, E2 reaction. So today we are going to start off with the E2 reaction. And of course, before we do that, let us go over the quiz problems that you guys have just taken. Okay, answer. Can you read this for us?
Methanol, CH3 reacts with 1-bromo-1-methylcyclohexane to get 1-methoxy-1-methylcyclohexane. Provide a mechanism for the reaction and write the rate logarithm.
Okay, thank you. Okay, so this question here is testing, of course, your knowledge of nomenclature. It is also testing your understanding of reaction mechanism. In this particular instance here, you have been given 1-bromo, 1-methylcyclohexane, and that will react with methanol to give 1-methoxy, 1-methylcyclohexane. So let us start by writing the structures of the starting material and the product, and then the reagent. Okay, 1-bromo, 1-methylcyclohexane, so that would be this here. Okay, so cyclohexane is the base name. Say 1-bromo, 1-methyl. Okay, that is the starting material. And in this case, we will call it the substrate. And then the reagent is methanol. And the product is this here. 1 methoxy, 1 methyl cyclohexane. So you can see here, this is a substitution reaction in which the methoxy group has replaced the bromine. So if I ask you this, what kind of reaction mechanism will this be? What kind of reaction will this be? SN1 reaction. Excellent. That is correct. This would be an SN1 reaction. Now, why did you say this is an SN1 reaction? Because the leaving group is attached to a tertiary carbon. Excellent. So once you see that, SN1 reaction takes place with a tertiary substrate in which the leaving group is attached to a tertiary carbon. So in this case, this bromine here is apparently the leaving group, and this carbon here is a tertiary carbon. So we say this is an SN1 reaction. Okay, so if this is an SN1 reaction, what is the special feature of an SN1 reaction in terms of the mechanism? What does it do? The reaction mechanism. It has to do what? It has to form, say that again? Form a carbocation, okay? So the unique feature of SN1 reaction is the reaction mechanism must go through the formation of a carbocation. That is the unique feature of an SN1 reaction. So therefore, if we have to write the mechanism for this, the first thing we do is we say this bromine here, this leaving group is going to leave. Let us. Okay, so the first thing that happens is the cleavage of the carbon-bromine bond. So you have to show the arrow showing an heterolytic cleavage. Those two bonding electrons will be going to bromine. Okay, and once you do that, then you form a carbocation. In this case, you form a tertiary carbocation. Okay, you form a tertiary carbocation in which this carbon here is positively charged, and of course, the bromide that has left is here, and that's your leaving group. So at this point, now the nucleophile, the methanol will be acting as a nucleophile, now comes in. Okay, the non-bonding pair of electron on oxygen will be used to attack this carbocation here, and then you form this. Well, let me change the color. At this point, this oxygen is positively charged. Okay? So now, what happens? No, I also want to use a different color here. Maybe it's blue. Okay. Now, at this point, the bromide here will now come, and simply the bromide will now act as a base to grab the proton and the the hydrogen-oxygen bond will break heterolytically, that the electron pair will go to here. Don't forget, we see I have one electron pair here, and so we therefore get this final product. Plus 8Br. Okay, and that final product is this one here. Okay, so what we've given you here is the reaction mechanism. At this point, we also want to let you know that this is the rate limiting step, at the point at which we form the carbocation. Okay, and because that rate limiting step is only involves the substrate, okay, the rate equation for this reaction here, for the SN1 reaction, will be this, because you are also told to write the rate equation. The rate law equation will be K, which is the reaction constant, multiplied by the concentration of the substrate. So in this case, you could simply write the substrate as Rx, or if you want, you could write substrate in brackets, okay? And that would be the rate equation, yes.
When do you know whether or not it's a network?
Wait, say that again?
When do you know whether or not it's running a network?
Oh, I see.
Yeah.
Okay. I showed you the enantiomer, okay, because I started off by showing you the stereochemistry of the starting material. Now, just to indicate to you what is the basic feature of the SN1 reaction, because in the SN1 reaction you form a carbocation. Okay. Now, because you form a carbocation, this here, the nucleophile could attack this carbon from both sides, so you form the enantiomer. So if I do not ask you to give the enantiomer, or if I do not ask you anything about stereochemistry or optical activity, you don't need to do that. Okay, if I simply just say here, from here, go to here, give me the mechanism. But if I do ask you a question that relates to optical activity, or something about racemate or enantiomer, then you have to show the stereochemistry. Because you notice here, I did not show stereochemistry here. Because this molecule is not optically active. This is not the chirality carbon. You see this, right? This carbon is not this molecule is not a chiral molecule. You follow that? Now, if it was a chiral molecule, and I wanted to show the fact that you are going to form an enantiomer, then I will give you a chiral molecule. Okay, so this is not chiral. Yes, go ahead. There's no, you cannot do stereochemistry here. You cannot do stereochemistry here, because this is not a chiral molecule. Okay. Okay. So anyway, so this is the reaction mechanism that we will require you to write. In other words, you show the formation of the carbocation. Once you show the carbocation, then the nucleophile, the methanol here, as the nucleophile comes in, attach the carbocation. In this particular instance, it also happens that the oxygen is still attached to hydrogen, so the bromine here comes here to abstract this proton and then you form your final product. Okay, which is this here. Okay, so let's go to the next one. By the way, the same mechanism will apply. Instead of giving you methanol, I could have given you water. It's the same mechanism. Okay, water could also act as a nucleophile. Okay, Victoria, can you read this for us?
Where the following compounds with respect to SN2 reactivity are A for most reactive and C for least reactive?
Okay, thank you. So in this case, what you need to do here, of course, it is simply testing your knowledge of whether you know what SN2 reaction, what are the conditions for SN2 reaction or SN1 reaction will be. So this is a fairly simple problem. Order this molecule here, relation to reactivity towards SN2 reaction. So we say order the following compounds with respect to SN2 reactivity. Assign A for most reactive and C for least reactive. So which would be the most reactive towards SN2 reaction? Which one? The middle one. Very good. So this would be A. So this would be A. And why? That is correct. Why? Primary. Because primary substrate, in other words, a substrate in which you have the leaving group attached to a primary carbon will be more reactive than the secondary substrate or the tertiary substrate. So which would be B? This one here? Good. C, of course, will be this one here. Okay. Now, supposing I ask you, instead of SN2 reaction, I say order this with respect to SN1 reaction. What would it be? Let me erase this. Instead of SN2, I say SN1. So what would be the order? What would be the order? A? Which one is A? The first one. Okay, good. So this should be A. That is correct. Why? Tertiary. Okay, tertiary carbocation is best for. Okay, very good. It's best for SN1 reaction. And B? And C, of course, is this here. Now, let me tell you why tertiary carbocation is not good for SN2 reaction. Okay. Supposing we have this, yes.
Will we points off for that? Because you definitely did not. Did you mention that?
Okay. Okay. Yes, I did several times. Okay. Now let me tell you why SN2 reaction is not good with tertiary substrate. Supposing we have this. Supposing we have that. And then we have this here. Supposing we have that. And you have your nucleophile. Let us use a generic nucleophile. Let's call it NU. Okay? Okay? The nucleophile has got to come from the back, from the opposite direction from where the leaving group is attached. In other words, the leaving group is here. The nucleophile has got to come from the back, from right here. When it does that, because of all of this alkyl group here, okay, they will crowd up this here, the approach to this carbon, because of the tertiary, all of the alkyl group that are attached to here. So this is what we call steric hindrance. As opposed to if you just have this. Say for example you have this. Hydrogen is a smaller atom than all of this alkyl group here. Don't forget the alkyl group. Let me actually do a little better than that. The alkyl group will look like this. So you have all of these. The alkyl group is much bigger than the regular hydrogen atom. The same thing on this carbon here. So therefore, the approach of this nucleophile to this carbon will be hindered. And that is why we say steric hindrance, okay? As opposed to, if you have this, if you have the nucleophile coming here, the approach to this will not be as hindered as in the case of the tertiary, because all you have is just hydrogen atom. So that is why tertiary tertiary substrates do not lend themselves to SN2 reaction. Okay? Of course, perfect for SN1 reaction because of what? The nucleophile doesn't have to attack. Okay? Before the nucleophile attacks, the living group has gone. Okay, so that is the reason why SN2 reaction favors primary or tertiary substrate. Okay? Okay, let's go to the next one. Okay, we say we'll do this later. Hopefully at the end of today we will do this. Okay, Camille, can you read this for us? Okay, very good. Thank you. Okay, so in this case, I do expect you to show some stereochemistry. It says consider the following SN2 reaction, provide a reaction mechanism and the rate law equation. Also now ask you, do you expect the product to be optically active or inactive? Briefly explain your answer. Okay, we've already told you this is an SN2 reaction. Okay, now you have to provide the reaction mechanism. Okay, so let us do the mechanism here. By the way, if this is a SN2 reaction, what would be the rate law equation? What is it? It depends on both the substrate and the nucleophile. In this case, this is the nucleophile here, the acetate ion. Remember, I believe I told you before that the acetate ion, which is this here, instead of writing it this way, to save yourself some time, we simply just write OAC. This part of the molecule is what we refer to as an acetic group. And we generally abbreviate that as AC. So that's where the AC comes from. And of course, because you have this oxygen here, it becomes OAC. So whenever you see the OAC, essentially you have the acetate ion. And that will act as a nucleophile. Okay. So what is going to happen here? The rate law equation you guys say will depend on the two, both the substrate and the nucleophile. So rate would be K multiplied by the concentration of the substrate. You simply just write Rx, or you could write substrate and the concentration of the nucleophile. Okay? So which means that if we draw the reaction energy profile for this, it will look like this. Okay. The reactants are here, the nucleophile also here, and the product is here. And you only have one transition state. Okay.
So instead of Rx, can you put RBR? Is that the same thing?
Oh yeah, that's fine. Yeah.
What about the nucleophile? Can we put in here?
Can you do what?
Put the nucleophile for the OAC?
Yeah, that's fine. Okay. Okay, so now let us do this. What is the reaction mechanism? Okay. We start with this here. Actually, it's a very, very simple reaction mechanism. Okay, where will the nucleophile come from? Okay, from what side will the nucleophile come from? From the side of the hydrogen or from the side of the leaving group? Where will it come from? Where will the nucleophile come from? What? From the side of the hydrogen, exactly. So now you have the nucleophile will come here, attack this molecule from here. Okay, from the back, opposite side to where the bromine is attached, and at the same time, while the acetate ion or the nucleophile is attacking that electrophilic carbon, the bromine will be leaving. Okay, and you can see here. So now, get this product. Now the hydrogen will now be here, and the acetate will be here. Okay. Now the next question is, don't forget at this point, if you determine the absolute configuration of this carbon here, let us see what is the absolute configuration of that carbon. Let's work it out. Okay, I'm standing between the bromine and hydrogen, and benzene is somewhere here. Okay, hydrogen is on my right, and bromine is on my left, and the ethyl group is below. Okay, so the assignment here, priority assignment will be A, B, C, and D. If you remember what we did when we did the assignment of absolute configuration. Okay, so what do I do? I move from A to B to C. I ignore group D. Okay. According to that motion, that should be what? R. However, because the group of lowest priority is coming at me in a Fisher projection, so I have to do the switch. I have to switch it. So that is actually S. Okay? So therefore, if you look at this, this is S. Okay, let us determine the absolute configuration of this here. Because the point is here, the SN2 reaction proceeds with inversion of configuration. With inversion of configuration. Okay, so let us figure this out. I guarantee you this will be R. Okay, so let us see here. Okay, so I am right here. I'm laying down between this acetyl, this my nose right there, looking directly at this here. So let us say this is this here. The benzene again is right here. The acetyl is on my right, and the hydrogen is on my left. The ethyl is below my chest. Okay, I do the assignment again. This is A, this is B, and this is C, and this is D. I make that motion. It's A to B to C. Ignore group B. The motion tells me it should be what? S. However, because the group of lowest priority, which is hydrogen here, is coming at me in a Fischer projection, so therefore I have to make a switch. The reason I am going through this, hopefully this is a review to all of you. I make a switch, and so therefore that would be, oh, I'm sorry, this is F. Let me take that back. Supposed to be S. The motion is S, so when I make the switch, to therefore be R. So this absolute configuration here is R. So you can see here, we started with a molecule that has an S absolute configuration, and we ended up with a molecule that has an R absolute configuration. And that is what we mean by inversion of configuration. Okay? Now the last question, it says, will this be optically active? Would the product be optically active? Anybody has an answer to that?
Yes.
Yes. Okay. Why will it be optically active?
Inversion configuration makes it active.
What do you see? Because it will not superimpose on its mirror image. That is the absolute condition. That is the absolute condition for chirality. Okay. However, I will say one more. Anytime you see a molecule that only has one chirality center, that molecule must be optically active. That molecule must be chiral. Okay? You follow that?
Yes. Yes.
You want me to write it down? Anytime you see a molecule that has only one chirality center, that molecule must be chiral. That means that molecule must be optically active. Okay? Okay, so let us go to the next one. I think we did all of it, right? Okay. We'll come back to 3. Let's finish today's lecture, then I'll come back to 3. Okay, let's just go back to today's lecture. Okay. Okay, so we told you we are going to start with an elimination reaction, which of course we started with the last time. Okay, so if you take a look at this reaction here, what we've done here, we've written this molecule here. This is what we call the sawhorse projection. Whenever you are writing this mechanism, particularly with respect to elimination reaction, it's better to start with sawhorse projection because you will see the stereochemistry better that way. See what is happening here. The base, this here, this B here is the base. When it comes to elimination reaction, we refer to the nucleophile as a base, because essentially what it is doing is abstracting a proton from another molecule. So the base is coming here, abstracting this proton here, or grabbing this proton here, and at the same time, the two non-bonding electrons that is used to bond between carbon and hydrogen comes here to form a pi bond between this carbon and this carbon. And at the same time, the leaving group is leaving. Imagine that this X is a bromine or a chlorine atom. The leaving group is leaving. So everything is happening at the same time. So this kind of reaction mechanism we refer to as a concerted reaction mechanism. Similar to what we had with the SN2 reaction. Because in the SN2 reaction, that is also a concerted reaction. Okay? Okay? So now, this will be your transition state, TS, and then you get this final product. You get this final product. Right here, at the point in which the base is pulling this hydrogen, and you are forming the carbon-carbon double bond, and the leaving group is leaving, that is your rate limiting step. So that is your rate limiting step. Therefore, what will be the rate equation for this reaction? What will it look like? The rate equation for this reaction, what will it look like? What would the rate equation, what will it look like? Exactly. In other words, it will be dependent on both the concentration of the substrate and the concentration of the base. Okay, so therefore it becomes K, use X for substrate and concentration of the base. So therefore we refer to this as an E2 reaction. We refer to this as E2 reaction. And that is where the bimolecular comes from. Okay, in other words, the step of this reaction mechanism, which is the limiting step that determines the rate of the reaction, depends on the concentration of the base and the concentration of the substrate. And that is why we call this bimolecular reaction. And that is where the 2 of the E2 comes from. Of course, the E simply says it is elimination. Okay, okay, so let us give you a few examples.
The arrows maybe to go both ways, right? The double arrows.
To do what?
The double arrows maybe to go both, the reaction to go both ways, right?
Yes, yes, it could go both ways, yes. So it could be an equilibrium reaction. Now, if we have to draw the reaction energy profile for this, for the E2 reaction, okay, will it be similar to SN2 or similar to SN1 reaction? Which one? SN2, exactly. So because there is no intermediate, here goes to form a transition state, and the transition state collapses to form the product. Here you have the Rx, the substrate, and then you have the base. Okay? And then this will be your product. Of course, here, the energy difference between the substrate and the transition state, that is your delta G transition state, which is your energy of activation. That is the amount of energy that is needed the minimum amount of energy that is needed before this reaction can go. Okay, so that is here. Energy of activation. Okay, so let us give you a few a few examples. E2 reaction. I want to show you the peculiarity of this reaction. I want to actually go through the reaction mechanism again. Supposing we have this. And here, look at the relationship between this hydrogen here and this leaving group. Okay? Of course, the base is here somewhere. Let us say we are using hydroxide as a base. We are using hydroxide as a base. So the base is going to come here. To grab the hydrogen. And then this bond is going to break heterolytically so that you form a carbon-carbon double bond right here. And this is leaving. Now, I want you to pay attention to the relationship between the stereochemistry between this hydrogen and this bromine. This is what we call anti-periplanar relationship. Anti-periplanar relationship between the hydrogen that is being removed, between the hydrogen and the leaving group. Now, if you do not have that arrangement, E2 reaction will not go. In other words, they are anti to each other. Okay? Periplanar means they are on the same plane. It's almost as though think of, let us say this is the hydrogen here. You see, they are on the same plane. Think of this as the hydrogen. Think of this as the bromine. They are on the same plane, but they are also anti to each other. That relationship must be there for the essence for E2 reaction to go. Okay. Okay, that relationship must be there. Okay. So that is what we refer to as anti-periplanar relationship. Okay. So, and then what do you get? You get this.
And you said that's mandatory for this reaction?
Yes, it is. I will show you when we get to examples, you see why. Okay, so now we get this product here. Okay, now, see this right here. Methyl is here. The ethyl is here. And this hydrogen is here. And this material is here. This is the product you are going to form. In other words, depending on the stereochemistry of the starting material, that will determine the type of product you form. Okay? Okay, so when you go home, you may want to determine the absolute configuration of this carbon here, and the absolute configuration of this carbon here. Okay, and you find that if you do use another stereoisomer, you will get a different product. Because the moment you pull this hydrogen here, you form this double bond, everything is going to be in place. This is going to leave. Okay? Okay, so now this relationship, the anti-periplanar relationship, must be there for this reaction to go. Okay, so let us give you a few examples. And I believe once we begin to show examples, you'll see exactly why. Supposing I have this. And I have this. Okay. Supposing I then ask you, I tell you this is an E2 reaction, okay, in which I use this as a base. I say, what is the product of this reaction? Let us number this. What is the product of this reaction? One, let's call that 1, 2, 3, 4, 5, and 6. Okay. Remember the six-step rule that we gave you? And what does that say? Anytime you want to form an alkene, the most substituted alkene will be formed, if it is possible, right? Okay. Based on that, if it is possible, that's what I said, right? What will be the product of this reaction? What would the double bond be? Between 1 and 6, or between 1 and 2, or between 2 and 3? Where? Between 1 and 2?
Yes.
That would be wrong. Because keep in mind, we told you the E2 reaction can only take place whenever there is a possibility of an anti-periplanar relationship between the hydrogen and the leaving group. Look at this here. There's a methyl group trans to this bromine. And this hydrogen is cis to this bromine. There is no way it's going to be anti-periplanar. So therefore, the double bond will not be here. So where do you think the double bond will be? Between 1 and 6, because that is the only time you could get any one of these two hydrogens to be in an anti-periplanar relationship with this bromine. You follow that? So that is why it is important to understand the mechanism of the E2 reaction, because there is a peculiar nature to that reaction mechanism. Okay, so therefore, the product of this reaction will be this. The double bond will have to be here, and of course this will still be here. Okay, that will be the product. That will be the product. Now, if ordinarily, if I did not show the stereochemistry, if all I did was just give you this, I just do this here, bromine is here, and hydrogen is here, no stereochemistry is shown. And then I say hydrogen is here, methyl is here. At that point, you will be correct to say the double bond will be here. Because at this point, I am not showing the stereochemistry. Because any one of this hydrogen could very well be anti to this here. Nobody is showing that. Okay, if I say give me the reaction product for this, then you could say the reaction product is this. Then you could follow the second rule, in which you now have this. As your major product.
How does the first one end the anti-periplanar?
This one cannot. You cannot get which or how is this one anti-periplanar? Because you do have two hydrogen here. You do have two hydrogen here. One of them could be trans to the bromine, and the other could be cis to the bromine. So the trans one will be the one that will be in the anti-periplanar with this one here. Okay? Okay. So anyway, this could be a trick question sometimes, so you need to pay very close attention to the stereochemistry of the product. Now the next question is, how do you recognize an E2 reaction? Okay, can you determine whether a reaction is an E2 reaction or E1 reaction? The conditions for E2 reactions. Unfortunately, the conditions are similar to the SN2 condition. Okay, one must be primary or secondary substrate. Okay, in other words, the leaving group must be attached to a primary carbon or a secondary carbon. Two, the nucleophile most likely is negatively charged. In other words, it is a strong nucleophile okay. Those are the two major conditions that you need to keep track of. Okay, now, what happens here, the E2 reaction and the SN2 reaction, they compete with each other. In that case, in many cases, we will tell you, if we have a problem for you, where there is a kind of borderline, whether it is SN2 or E2, we will tell you whether this is an SN2 reaction or whether this is an E2 reaction. Okay. Very often, when you have a problem that we want you to solve, we will tell you whether this is an E2 reaction, okay, or whether this is an SN2 reaction. Okay, that way you will not be confusing SN2 with E2. Okay? Huh? Go back. Okay. Let us do the last reaction mechanism, which is the E1 reaction mechanism. Elimination, unimolecular, referred to as E1 reaction. Okay. Now the E1 reaction, of course, is similar to the in a way it would be similar, the reaction mechanism would be similar to that of the SN1 reaction. The difference is this would be elimination reaction. Both the SN1 and the E1, they go through the formation of a carbocation. Okay, so therefore, let us try with this molecule here. Supposing we have this. Supposing we have this. In this E1 reaction, and of course if we say we have this here, the base is coming in as an hydroxide, this hydroxide. The bromine will leave, this will go, and then we form this. Okay. You're also going to form this. From these two are thing here. Notice here, this will be trans, right? And this will be cis. So how does that happen? Of course, in the case of the E1 reaction, let's write the mechanism. The first thing that happens, okay, let us write this out again. Yes, from both of them. Okay. The first thing that happens in E1 reaction is the cleavage of the bond between the carbon and the leaving group. Resulting in the formation of a carbocation. Okay? And this here is the rate limiting step. You notice right here, just as in the case of the SN1 mechanism, you do not need the the base in the rate limiting step of the E1 reaction. So we now form at this point, we now form this carbocation. Okay? This carbon of the carbocation is an sp2 hybridized carbon. Which means that this here is flat, okay? Right there, it's planar. The stereochemistry around this carbon here is planar. Also, because we are forming this carbocation here also, it is possible we could get, remember when we did the conformation of alkane, we could get a rotation here of this carbon-carbon bond. You could get a rotation here. Supposing you get that rotation, keep in mind what we want to do is to explain how we form these two products. You could get that rotation, and now you get this. Now if you get that rotation now, what you now get, you will now get this where, actually let me make this so that this will be very obvious.
What is that, can you use the second step? What's that little arrow right there?
Just a minute. Let me make this so that this is going away and this is here. Okay. Now if you do almost like, what are you doing here? See, this is what we're doing. Because a carbon-carbon bond, you could rotate a carbon-carbon bond. Right. So if you rotate it, that's what we've done right here. Okay, so this is the rotation that we are doing here. If you do that, then what do you get? You now have the metal on this side, and the metal is on that side, and the this is here. Okay. Now see what is going to happen now. If the base now comes in, let me take this off. The base comes in, pull this one off, right? And this goes here. See what you get? You get this. On the other hand, if the base comes in, pull this hydrogen off, and this comes here, form a double bond. This is positively charged. You get this, and that's how you get those two products. But the most important point we made here is that in the E2 reaction mechanism, you form a carbocation. Okay? You form a carbocation. And the rate law equation for this reaction will be what? The rate law equation will depend on only the Rx, because we form the carbocation before the base comes in. So therefore, the rate law equation for this is this here. Okay. Okay. In other words, the rate of this reaction depends on the concentration of the substrate. Yes.
So you said in this, right after the rate limiting step, it has a charged particle. You said it was planar.
Mm-hmm.
Why is the stereochemistry step?
Yeah.
No. Okay, this is what I'm showing you. You are looking from here. This is planar. This carbon is flat. It's planar.
Right.
Okay? This is the angle you are looking.
Okay.
One is coming at you, one is going away. That is possible.
So how is it? Sorry, I didn't see how it was planar.
This is planar.
Those three.
Okay? Everything attached to this carbon is on the same plane. Okay, think of this as an atom. This is an atom. All of those atoms are on the same plane as this carbon. That's what we mean by planar.
Okay. And
Okay.
what is coming out and going into? Which ones have stereochemistry in this example?
Which one is, say that again?
Have stereochemistry. Okay, keep going.
Okay. Now, so we say this is planar right here, right? So therefore, you could rotate this bond.
That's still planar then.
Yeah, it's still planar, but when you rotate it, see when we did the rotation right here, when you did the rotation from here to here, look at now, this metal is on this side, and this is on this side. Okay? The point is we need to explain why when we did this, we got this product or this product. Because now if you remove hydrogen from here, with this conformation right here, okay, this metal and this metal will be on the same side.
Oh, so it's
okay? And if you remove the hydrogen with using this conformation right here, this metal and this metal will be opposite to each other, and that's how you got it. Okay? So, okay, what are the conditions for E1 reaction? What are the conditions? The most important condition is that the substrate must be a tertiary substrate. Okay, one, substrate must be tertiary, or a substrate that could generate a stable carbocation, or a substrate that could generate a stable carbocation. Okay, for example, this here. This here could be, this could be an E1 reaction. If I tell you this is an E1 reaction, give the reaction mechanism. What is going to happen? You form a carbocation on this carbon. If I say give me this is an E1 reaction and give me the mechanism. Okay? What will be the mechanism? You lose the leaving group, you form this carbocation, which will be a benzylic carbocation. And then the base will come in to remove this hydrogen here. In other words, this is what you get. Even though this is a secondary substrate, it still goes to the formation of an E1 mechanism. Okay, because you could get this. And that's your benzylic carbocation. Okay, now the base will now come in. Grab this here, and then this here, and then you form the product. So this could be an E1 reaction mechanism, even though you are starting with a secondary substrate. Okay? Okay, folks, we are going to finish up all the problem set in where we meet on. I believe we actually did all of the problems in the last exam, in exam number 3 from 2012. All of those problems have been done already. We did them in all of the quizzes. I don't think you guys already noticed that. The only one we did not do is the number 3 that I told you what to do. We will do that on Sunday. And we will also go to the rest of them for the benefit of all of you on Sunday. Okay? So I will see you on Sunday at 8 p.m. for those who can make it. Oh, by the way, for the E1 mechanism, reaction energy profile for this is this here. In which you have your carbocation right here. Okay, so you have 2 transition states. Okay, and this is your substrate. And carbocation here, and also your base is right here. And product. Okay, so we'll see you guys on Sunday. You finished?
Look at